So thank you for the introduction, John. So I'm going to talk about our experience over at Tokyo Institute of Technology with accelerating POSITs and combining them with OpenCL for FPGAs. So this is what I'm going to talk about, and I'll start off with the introduction and motivation. Most of you probably know this, but the notch scaling has broken down, so we cannot longer rely simply on frequency and voltage scaling, and we don't know how much longer more will continue, Moore's law. Which means that we have to go back and look at all the decisions we've done with respect to compute architecture and see how to continue, how to improve them. This has already materialized itself when going from single core to multi-core to many-core, and see on nice landing, etc., etc. We're starting to see heterogeneity, and the future might even go with quantum computing or morphic computing, etc., etc. Now, one of these decisions that we need to look at, and we need to go back, is floating point calculations. Why? Because if we can improve floating point computations, we can potentially get better solutions, better accuracy, better performance. And one of these candidates right now are POSITs. There are indications that POSITs can indeed be better than alternatives. However, in my opinion, this is only the tip of the iceberg. We need far more empirical data to draw more conclusions, right? We need to position POSITs against IEEE 754, the 754 format, and compare it. Compare it, what gains do we get? What are the accuracy gains? What are the performance gains? And quantify all of these gains to finally see if we should continue pushing this forward or not for a lot of applications. Deep learning, stencil computation, molecular dynamics, etc., etc. The only problem with this is that right now, even though the POSIT libraries are starting to mature, they are slow. They are really, really, really slow. And that is because they're emulated using existing general purpose processors. And often you get megaflops of performance, or even lower than that. You can't test real use cases, drive real use cases with real data with megaflops of performance. It's not going to work. So how can we accelerate POSIT computations? Well, what I'm going to use, and what we've seen earlier as well, is to use fine-grained reconfigurable devices such as field programmable gate arrays. Field programmable gate arrays. Shortly, FPGAs. These are devices that contains a lot of reprogrammable logic, compute parts, and routing parts, right? So what you do is that you have your, you want to implement some kind of Boolean functionality, you want to have some logic, and you can reprogram these lookup tables, connect them through a reprogrammable routing, connect them to each other, and start having behavior as if you were executing something in ASIC, right? Historically, these were actually used to simulate your design before you sent it off to fabrication in order to spot bugs, right? Historically, they've also been used in embedded electronics, such as for automobiles, military uses, telecommunication, and low volume consumer electronics. Today, they are actually a force in their own right. FPGAs today can reach very high, or again, it's to me at least very high clock frequency, so between 200 and 800 megahertz isn't uncommon. We have a large amount of compute on chip on these FPGAs. So the latest Stratix 10 devices from Intel can reach up towards 10 teraflops of performance, of single precision performance. Xilinx is, of course, offering similar devices. We have millions of gates. And we can use these compute capabilities to accelerate POSIT computations. So what we did, and you can actually find more information in a different paper here, is that we created a generator, a POSIT generator, where a user specifies the size of the POSIT, 16-bit, 18 bits, 10 bits, 127 bits. He also specifies the exponent size or exponent bits and some other functionalities, and automatically our tool will generate operators, POSIT arithmetic operators for that requirement that the user specified. This is all very good because you get VHDL code for POSITs. How many here can program in VHDL? Low-level VHDL, are comfortable with that. Excellent. So I see 3. So point is, if I take VHDL code generated by my POSIT generator and give it to a software programmer, he will give a very good look at me like, well, I don't know how he would look at me, but not very nicely, I'm sure. The problem is, yes, we have these, but no one can use them. There is a programmability gap that needs to be resolved. We need to close that gap. And the way I see it is 2 options. One option is to take your favorite computer architecture, MIPS, RISC-V, Spark, OpenRISC, and essentially rip out that traditional IEEE 754 floating point unit and plug in the POSIT unit. A very nice case. This would be the ideal case. Why? Because you'd have access to all that software stack, hopefully your operating system, etc., etc. The only problem is right now, that's also a very invasive way of doing things because you have to port all of that software stack. You have to port all of those libraries, the standard C libraries, all of that will have to be ported. So what we're proposing is instead to integrate the POSIT components into a parallel programming model or language. Something that is closer between the language and the hardware, that do not rely on tons of software stacks. And one such example is OpenCL, right? Which is also supported by most of the vendors nowadays. So, OpenCL. How many have done something in OpenCL? Probably a lot. No? Oh dear. Oh dear. A handful. It stands for Open Compute Language, and it's a programming model that's based on the subset of C that's supposed to target a number of heterogeneous devices. So you write your code once, and you can have it running on CPUs, GPUs, and today also FPGAs. You can see a very short example here on the right, where you have a vector addition. Your input arguments or input parameters are three pointers, and basically you spawn a lot of threads. Each thread, you get the thread number of which thread is currently executing, and you proceed to add the indices from the 2 vectors and store it from the 2 vectors A and B and store it to C. It's very simple. And basically the programmer is responsible for writing the kernel, the compute part of the application, and also the orchestration. So usually the compute part is what is running on the accelerator, on the GPU or the FPGA, while the orchestration is running on the host general purpose processor, and involves things like memory transfers, kernel invocation, allocation, etc., etc. Using OpenCL for FPGAs relies on high-level synthesis. So most OpenCL implementations for FPGAs uses high-level synthesis, which means that the compiler transforms your OpenCL code into dedicated hardware. There are 2 ways of programming. One is the thread-level parallelism view, in which you control a large number of threads and expose parallelism through those threads, while the other way of programming OpenCL for FPGAs is through the so-called single work item model, where you just get one thread, but instead you're focusing on exploiting parallelism through various instruction-level parallelism methods, such as loop unrolling, loop pipelining, vectorization, etc., etc., etc. So the way that we do combine POSITs and OpenCL is that these OpenCL for FPGA tools allows us to call RTL code, that is VHDL code, from the OpenCL C code, right? Which means that we can replace parts of the computation through calls to a POSIT library that will be inserted into that very deep pipeline that is generated by the high-level synthesis tool. So what we're actually proposing is something much more complex. The ideal scenario would be that we have the user kernel code here and the requirements, and that we feed the OpenCL code through a source-to-source compiler that would replace the floating point, the traditional single and double IEEE 754 floating point arithmetic, with calls to our POSIT library automatically without any user intervention. We will have the POSIT generator tool, create the hardware component, assemble it into a library, and then merge it all together and feed it into the high-level synthesis tools. However, right now, we only have the red part. We don't have the white part yet. So, what can we expect from having POSITs execute on OpenCL on FPGAs? So we're going to give you a short example application here, what we have done, just to give you a metric of what kind of performance you can reach. And we're going to have a board. The FPGA board is a Theresig board, Theresig D5 net board. It uses a Stratix 5 board, so it's an 8-year-old board. Please have this in mind. 8-year-old board with 2 banks of external DDR3 memory. We used Intel FPGA SDK for OpenCL. And we're going to look at a 2D stencil application, where it's a first-order star-shaped stencil with a grid size of 128 x 8192. And for this particular experiment, we are having 32-bit POSITs with 3-bit exponent. And we're going to look at the performance in terms of POSITs operations per second, okay? Or POPs, as so many people have said before. Why stencils? Because it's a crucial application. It's a very important application used in HPC, very many different fields, right? And now lately, we're also seeing that in convolutional neural networks, at least for the front-end part. So how does it work? You have a stencil operator. It is sliding across a mesh, a 2-dimensional mesh in this case, and each point in the mesh is calculated with a weighted sum of its neighbors, right? And the shape of the stencil, the order of the stencil, dictates the number of neighbors that is needed. This is one of the applications that we believe that POSITs can actually give us a good benefit, because for 2 reasons. Either you get a faster convergence for your problem, or you can reduce the precision while still, and get better performance, essentially. So the first naive version, as you can see here, on the left, this is our IEEE 754 version for the compute part alone, right? So we have 2 iterators, IX and IY, that are iterating over our 2-dimensional grid, and we're taking the central grid position and its neighbors, multiplying with the coefficients, and then storing it into an output array B. And to the right here, we see the same version, but with these calls to the POSIT library. Still OpenCL code, not much has changed. And this is pretty much the naive version, because it has a low compute per memory access, right? So, and what we get, so, okay, the performance here for this naive version, you see on the right-hand side, the stencil performance in terms of giga POSIT operations per second, right? We're reaching roughly 2 giga POSIT operations per second. With respect to the area utilization of the FPGA, we're roughly using 25% of the logic, roughly 18% of the memory blocks, and 2% of the DSP, the compute blocks, okay? So let's see how we can improve this. One way is to have a shift register, right? We can exploit locality, we can keep data on chip, and remove a lot of those loads and stores. We needed 5 of them per stencil operator to merely 1. That is the blue part that is sliding here. So we have a FIFO that we continuously push in work and keep data on chip. This is very good, because it reduces the block RAM usage and also makes it less memory bound. So what is the performance of this? You can see that we got not so much, but a little. We got some 0.5 gigapops per second extra. Not bad, not bad. Note that we reduced the amount of memory blocks that are used, and also the total number of logic, while keeping the DSP blocks the same. We haven't changed that. Let's continue. Vectorization. We can compute multiple grid points in parallel at the same clock cycle. We can vary this from 1 to 2 to 4 to 8 to 16. And the reason why we do this is that when we compute one stencil operator, we're just reading one POSIT and writing one POSIT. Our two banks of DDR can sustain far more than that. So we have ample room to actually vectorize our code. So if you look at how vectorization happens, what it gives us, we're starting to see some performance now, right? So yes, we're increasing our resource utilization. We're increasing, note here, the DSP blocks are increasing. And we're up to close to 12 gigapops per second. The final optimization I'm going to talk about is something called temporal parallelism. And for more information about this, we have a very nice paper over at FPGA, which you can listen to this about, or read more in detail on all the hairy details and how to optimize this further. But we can compute multiple time steps. So we can compute the stencil for one of the iteration in time step 0, channel it through, and compute the second time step before writing it back to external memory. And of course, the degree of temporal parallelism dictates, the scaling. And we get nearly linear scaling, but it's subject to how good we use the memory efficiency, the bandwidth of memory. And also, this is a very good way because it can scale across multiple FPGAs. So just having a temporal parallelism of 2 gives us lower, let's look at the right slide first. Having a temporal parallelism of 2 gives us nearly 22 gigapops per second, while being at the same level of resource utilization as our 16 vector version. So what we did was we decreased and had a vector size of 8, but doubled the temporal parallelism, right? There is more information here. This is the final result slide. And what you can see here is that the frequency, represented by a line associated with the right y-axis, reaches and continuously is on 300 megahertz. That's not a low frequency. That's very high. Furthermore, for the sake of my amusement, we tried the very same stencil application in software using a certain implementation. I'm sure there are better ones out there, but this personal one, it reached between 3 and 9 megaflops, while we reach up towards 22 gigapops per second. So what does this tell us? I think we have shown that OpenCL for FPGA is a very good candidate to explore POSITs. We can write it in C. We know how to write C. And we can compile it down and still get reasonable performance. These are the kind of performance that we need to start looking at real problems, right? And in this case, I showed for a stencil application, we reached 22 gigapops. There are still improvements to be done for this one. We can likely get up to 37, 38 gigapops. It's still roughly 3 to 4 times less performant than their floating point correspondence. Nevertheless, it's very good performance. Future outlooks, there is a need for a source-to-source compiler that automates this connection to the POSIT library. And there are still units that we're missing, exponents, square root, and many more. So with that, I will end my talk. Thank you.
Thank you very much, Artur. That was very interesting. And I think we have a very good idea of what we can do with POSITs. So let's You're seriously going to build an EXP unit in hardware?
Well, could be possible. Yeah, it's possible. Why not?
It's expensive.
It is expensive. It is. Yep.
Most people do their special functions in software. A square root you might want to build. That's not so expensive. That's a good thing to have. But
X power, all of these are definitely needed, I think.
okay. Well, questions? Yes.
So I can't say really, I understand it very well.
Okay.
But can you just confirm that the host processor is running serial and you're doing something like factorization in the FPGA?
So if it's running in serial, well, it's running serially, but it's running multiple iterations in parallel. So we're using loop unrolling, we're using loop pipelining. Think of it as having a deep pipeline. A deep pipeline. Think of.
Yeah, you're just saying it's the traditional CPU instruction level parallelism.
But made for hardware. So whatever you're unrolling is actually manifested in hardware as a dedicated unit with a very deep pipeline, right? So if you look at, for example, this code here, let's take this for simplicity, would have a pipeline where all of these operations, aside from the memory operations, can be executed, simultaneously. You have a pipeline that is, say, 300-400 cycles deep, and you would insert one iteration every cycle, and all of these would execute in parallel to each other at different pipeline stages while being fed by the external memory, yes. Let's take it offline. I can give you a more detailed view of it then, yeah.
So is it possible to do in parallel? Right. I mean, different CPU cores run different threads, and then maybe you have different FPGAs for every thread.
This is not doing any CPU activity. There is no CPU here. It's only the FPGA.
Yeah, but the next stage you have to do in parallel, right? On the host processor.
Which stage?
It's all data flow
Yeah.
in hardware. FPGA is data flow in hardware. There's no CPU.
I don't need a CPU for all of this. None of this. It's all done in the FPGA. If I wanted to, I could likely not even, no. Everything is done in the FPGA. Yeah.
Other questions?
Will your design communicate with the computer to get data from computer and do the calculation and send it back?
It's communicating the computational part. All the data is already on the FPGA, on the DDR3, right? Yes, I use a computer to get the data there in the first place, but that need not be the case, yes. But yeah.
Is it possible to design an interface based on and connect the interface to your design in OpenCL? For example, USB or PCIe or?
Well, this particular FPGA card that I have is sitting on the PCI bus, yes.
Okay.
Yeah.
Okay, thank you.
Any other questions? I have one more. If someone wants to get I know that there is a demand out there to do a side-by-side comparison of floats and posits, and as you say, you've got to get the speed up so that you can even make sense, because there's such a huge hardware advantage of the existing IEEE floats. They've been around for too long. Is there a way to make your stuff available in one way or another?
It will be available. If someone is interested already now, then just send me a mail and I'll send you the generated, the components such as the VHL component. The code for the generator, I will have to polish a little bit before I release, but yes. If anyone's interested, I can send you the VHL code over for whatever.
I'm thinking more at the level of a commercial thing. I mean, Amazon Web Services will let you rent time on an FPGA-enabled CPU. And so somebody could make a business of supporting your software or your design, and it could be available to anybody, just anybody with a web access. Yep. They could do their experiments and try it with floats and try it with posits. And if there are comparable levels of technology and you know that their speed is, then they could start seeing, is it accurate enough?
Yes, right.
Yeah. That's a good point, John, because there's also, to a fair comparison, you have to also have a full IEEE. So in order to do a fair comparison, you also have to have an IEEE FP floating point generator, which is, Alter basically He didn't write, but there are public ones available.
Yes, there are some.
So, so if you can, do a side-by-side comparison by generating this IEEE floating point and generating POSIT, and then doing the comparison, that's a fair thing. To utilize the DSP floating point units with in the modern like static stem
Yeah.
would not be a fair.
Right,
game. So,
yeah, a lot of people strip out all of the ugly rules of IEEE when they go to put things in DSPs.
Yeah.
No gradual underflow, no funny rounding modes and things like that, and that makes them look like a real winner because you get rid of all the junk. But if you really do a full IEEE implementation, and it's available open source mainly for the 32-bit and 64-bit. We tried to find it for 16-bit, and no one seems to have IEEE rules applied to 16-bit. It just, those two don't mix. If you're all the way down to 16 bits, you probably don't want all the garbage rules. But then that you can do the fair comparison. I really would like to see more in the way of a full IEEE FPGA 16-bit, because low precision POSITs are really interesting. They're very powerful, and they can take over a lot of 32-bit applications, and that's when you get incredible speed. If that's it, I think let's thank our speaker again.